Okay, so welcome back. This is example number 2 of graphing rational functions. Let's start off with this function here. Let's start off with this function here. F of x is equal to x cubed plus 1 over x squared minus 1. Now, what we want to do, the first thing, like we talked in our steps, we want to find our domain restrictions, or we can call them our holes. We want to find that. The second thing, we need to find our zeros. Third thing, we need to find our horizontal asymptote and our vertical asymptote. And then the fourth thing is left to just graph. And like I said, we'll graph using the calculator and we'll graph by hand. So these are the four different steps, that we'll take to go to solve this function, to graph this function here. So let's go ahead and substitute for f of x. We're going to go ahead and write y equals x cubed plus 1 over x squared minus 1. And what we're going to do, we're going to factor this. And now the reason we're factoring it, we're actually reducing this so we can reduce this rational function so it'll be a little bit easier to graph. But what you'll see is when we reduce it, it'll help us to get this domain restrictions. So this is actually the difference of, the sum of a cube. So what we would actually do, this would be x plus 1 here. And then over here we'd have x squared minus x plus 1. Minus x plus 1. And if you don't remember the difference of the sum of the cubes, we'll go over that in a later video. I don't have one on that just right now. Now this is just the regular difference of squares, so we'll just put x plus 1 and then an x minus 1 here. Now after this, what we'll talk about, we looked at last video, we said anytime we have something common, we're going to go ahead and take those as being our holes when we solve that. So this here would be our holes, and we're going to solve. Once we solve for this, that'll give us our holes. So to make this more clear, whatever's common between your numerator and your denominator, or common in p of x and q of x, what we're going to do, we're actually going to set that equal to 0. So it will be x, let's see, the holes, give me a second. So actually the holes would be equal to x plus 1 is equal to 0, and we get x is equal to a negative 1. That will be the hole in this graph here. So we're going to go ahead and write that up here. X is equal to a negative 1 as our hole, and we're done with that one. Next, what you're going to do, you're going to simplify, right? So we're going to cancel out this numerator and denominator. We're going to cancel those out. After that, we're moving on to finding the zeros. Now, if you remember the zeros, p of x is equal to 0. That's how you find the zeros. 0 is equal to p of x is equal to 0. And what do I mean by p of x here? I mean by this numerator of this function. So basically setting the numerator equal to 0. That will give me the zeros of my function. So let's go ahead and do that here. The numerator we see here is just now x squared minus x plus 1. So x squared minus x plus 1 is equal to 0. Because remember, we canceled out this first, we canceled out these two commons here, and now this is the only numerator that's left. So that's what we need to go ahead and set equal to 0. But if we see something here, we see that this function has no real solutions. And I'll teach you why. If we take the discriminant, here, we see that this function, we'll plug it in here. Let's see. The discriminant is b squared minus 4ac. And remember, when you substitute this in, it needs to be less than 0. I'm sorry, greater than 0. 1 second. It needs to be greater than 0 in order for it to have a real solution. So let's go ahead and see if that actually does have a real solution here. So we'll take b squared, which you understand b is 1. That's b. And then 1 is a. And then this is also c. So let's go ahead and substitute that in. We have b squared minus 4ac. So we have 1 squared minus 4 times 1 times 1. We'll get 1 squared minus 4, which will be 1 minus 4, which will be equal to a negative 3, which is not greater than 0, because that is negative 3 is less than 0. So this tells us that we have this tells us that we have no real solution here. That's what that tells us. We have no real solution. Okay, so this tells us that we have no real solution here. And what we're going to actually move on to is I won't really tell you why the discriminant tells us if we have a real solution or not right now, because it's not going to do us any justice in this video. Just know that you use a discriminant to figure out if this has a real solution or not when you can't clearly see it. Okay, so let's move on here. Let's go to the next thing that we need to find. So what do we say for our zeros? We say that we don't have any zeros right now. There are no real zeros of this function. So there are no real solutions. So we're not going to cross the x-axis here. So zeros, we're going to go ahead and write that in. We're not going to cross So we're not going to cross our x-axis. That's what we have to see here. So none. Okay? There are no non-real solutions here. Let's make sure we emphasize that they're non-real solutions. Okay, next, what we'll do is we will go ahead and find the next thing, which is a horizontal asymptote. Horizontal asymptote. Now, if you remember when I told you guys last time, it depends on the powers, right? So let's look at our equation. It depends on the degrees of P and Q. Now, this degree here is P of x. This is P of x, of course. And that degree is a lot higher than this degree. The degree of this polynomial here is 2. But the degree of this down here, this binomial, what is it? It's 1. Okay? So we see when this is greater than this, we usually say there's no horizontal asymptote. Okay? So let's go ahead and write that down here. So since, we'll give a little reasoning behind that, since P of x, since the degree of P of x is greater than the degree of Q of x, no horizontal asymptote. Okay, so let's go ahead and write up under horizontal asymptote, we're going to write none. Okay, vertical asymptote. Now, vertical asymptote, remember, that's where my function is undefined. And you remember we set the denominator equal to 0, so it'll be x minus 1 set equal to 0. This denominator, Q of x, we'll set that equal to 0, which will be x minus 1 is equal to 0. I advise you guys to write down the steps from the last video, so you'll have them. So we'll take x minus 1 and set it equal to 0. And, of course, we'll have x is equal to, oh goodness, x is equal to a negative 1 here. Positive 1 here, sorry. So we'll have x is equal to positive 1. Okay, that's my vertical asymptote. And we'll go up from here. Vertical asymptote will have x is equal to a positive 1 there. And last thing, we're just going to graph it. So basically, we have everything that we need. Let's go ahead and put this bad boy in a function here. Okay, so we start off with the graph. And what we'll do is we'll graph our vertical asymptote, which is at x is equal to a positive 1. So that'll be about right there. We'll graph that down. Okay. Then after that, what we will look at would be our function. How does this function actually behave? Now, we understand that these functions hug these vertical asymptotes. Now, we don't have anything else like we did in our last video, like another horizontal asymptote that we could use, or we don't have a 0 that we know it needs to cross. We just really have our hole and we have our vertical asymptote. But we can solve using that. Now, you can always use the graph. Use the chart. But we don't need to really do that because we understand that this is going to hug this graph, right? We understand that's hugging that graph, and we're going to go somewhere out that way. And then coming from here, we're going to hug this, and of course it's going to go out that way. This graph here should actually curve a little bit down there. We talk about end behavior, but you guys remembered that. So, okay. So this is just about a rough sketch of this graph here. But now we do remember that we have a hole here. So we need to go ahead and put that hole in. And that hole is at x is equal to a -1. So that'll be about right here, just estimating. We'll go ahead and align that as the hole. X is equal to -1. That's the hole in my graph. And we'll label that as the hole, or the domain restriction. So how would you generally write this equation with this domain restriction? Well, it'd be y is equal to x squared minus x plus 1 over x minus 1, where x is not equal to a -1. That's how you would write this domain restriction here, that hole. But now also, x cannot be equal to a +1 because that's our vertical asymptote. That value is undefined at that point, right? So let's go ahead and put it in this graphing calculator here just so we can see exactly what we're looking at. So turn this on here and we would type in, let's clear that. What is this equation? We would type in, let's see, x squared, x squared minus x plus 1. We'll close that parentheses, divide it by an open parentheses, x minus 1. That minus 1, x minus 1. Close it, and we'll graph it. Okay, so as you see here, this is this vertical asymptote here, and this function, it hugs it and it goes out like that. And then this function coming from down here, same thing we have here, it comes and it goes straight down like that. I think we can draw this a little bit better now that we see this graph. But as you see, it's just a rough sketch. So it's the same sketch. It's just that, of course, the graphing calculator will give us a better sketch, but by hand, we're just doing a rough sketch. So it's nothing too tedious. Let me go ahead and redraw this here so we can have a better picture of how it should look now that we actually know from the graphing calculator. Okay, so it would more than likely, let's get this purple here, that's fine. So like we said, it's going to hug this graph, hug it, and then it goes up. But this one here, it should be a little bit wider than that, at the bottom. But like I said, I'm not going to try to make it too perfect. We're just going to make it, just look here, rough sketch. So then we're going to come up, we're going to hug this graph. Oops, I'm doing it again. We're going to come up, hug this graph, and we're going to go out like that. This pen is right in front of me. We're going to hug out like that. And it's going to start to curve down. So as you can see, we hug this vertical asymptote and then we curve out. Hug this and we curve out. Now remember, this is not touching it. Not touching. It can never cross a vertical asymptote. Horizontals, yes. Verticals, no. Okay, so this is the rough sketch of this graph here. And stay tuned for the next video.